Welcome to a new lesson of heat transfer. Today we're looking at different mechanisms of heat transfer. We know that heat can be transferred by conduction, by convection, or by radiation. So if you have a heat transfer by conduction, what happens is that particles at higher temperature transfer thermal energy to particles at a lower temperature. And this happens when there is no velocity of bulk motion of any sort. Instead, if you have convection, we have transfer of thermal energy between a solid and a fluid that's in bulk motion. In the third case, radiation, we have energy emitted by matter in the form of electromagnetic waves. So now let's look at first conduction a bit more in detail. And so conduction occurs in gas, liquids, or solids. So in the case of gas and liquids, the molecules of the gas of the liquid collide and heat is also diffused, and this happens because the particles are in microscopic motion, and this motion is random, so we don't have a bulk motion, so the velocity is zero. Instead, for solids, conduction occurs because of vibration of the lattice and also because of the motion of free electrons. Conduction depends on the properties of the material, on the geometry, on the thickness of the material, and of course on the temperature difference. So the question is how conduction depends on these quantities. So we can consider one of the simplest cases in conduction. So we have a thin wall, and to simplify the analysis, we consider this wall to be thin with respect to the perpendicular direction of the flow of heat. And we suppose that this wall has a thickness delta x, and the left surface of the wall is kept at a fixed temperature T1, and the other surface on the wall on the right is kept at a temperature T2. So what happens is that if the properties of the material are uniform, then the temperature decreases linearly from T1 and T2. And heat flows from the temperature T1 to the point of temperature T2. So it's indicated here by Q dot. So in the case of steady one-dimensional heat transfer with constant property, Q dot is equal to K A T1 minus T2 divided by delta X, where A is the surface area of the two walls, K is the thermal conductivity, and it measures the ability of the material to conduct heat. So we note here that Q is obviously higher if we increase the thermal conductivity, if we increase the area, obviously, if we increase the difference in temperature, T1 minus T2, and we have more heat transfer if delta X goes to zero. We also note that the absolute value of the temperature doesn't matter. All it matters is the temperature difference. If we now take the limit of delta X going to zero, So we can imagine that the thickness of the wall is going to 0. So we have a very small thickness. So we can study a local heat transfer. And then the delta T over delta X becomes the derivative of the temperature with respect of X. So we obtain what's called the Fourier's law of heat conduction, where Q dot by conduction, it's equal to minus K A dt dx. So remember, K is the thermal conductivity. So Fourier's law was written by Fourier in 1822. What's important to note here, we have a minus sign. So this negative sign is due to the second law of thermodynamics, which means that Q flows in the direction where the temperature decreases. So let's look at this concept of a negative sign a bit more. So we take a coordinate system X, and we imagine then the temperature decreases as X increases. So in this coordinate system, dt dx, the derivative of the temperature with respect of X, is negative because the slope of this curve is negative. But we observe that Qx is positive in this coordinate system. And remember, Q is, in general, a vector. So the minus sign refers to this coordinate system. If you flip the coordinate system, so X instead is going to the left here, then dt dx would be positive and Q would be negative. So everything would be consistent. So we have introduced the concept of thermal conductivity K, and so we said that that expresses the ability of the material to conduct heat. For example, if you have water, we have a K of about 0.608 watts divided by meter Kelvin. But if you have instead iron, then we have K equal 80.2 watts divided by meter Kelvin. So in this case, we can see that iron is a much better heat conductor than water. So if we have a high value of thermal conductivity, we have a good conductor of heat, whereas if you have a low value of thermal conductivity, we have an insulator or a very bad conductor. One way to find the thermal conductivity of a material is to carry out an experiment. So in this case, we have a solid here, and the height of this solid is much larger than the thickness, delta X. And we have some electric circuit on the left. Everywhere is insulated. So, of course, the electric circuit will warm this part of the solid, and the temperature will be T1, so we can measure that temperature. Whereas the temperature on the other side of this wall will be T2. Then we know how much heat we inject into this solid, so we know Q. We know everything because we know the area, we know delta T, we know delta X, we know Q. So we can use the Fourier's law of conduction, and we can find K. Note here, I didn't put the minus sign because I'm taking the absolute value. So as a general rule, we have usually that the thermal conductivity of a gas is smaller than thermal conductivity of a liquid. That's smaller than the thermal conductivity of a solid. So remember, in gases or liquids, the heat conduction occurs because molecules collide and we have diffusion of heat. Whereas if you have a solid, heat conduction is due to the vibration of the lattice of crystal and because of the flow of free electrons. In general, the thermal conductivity depends on the temperature, but in our course, we can assume the thermal conductivity K to be a constant most of the time. I've sketched here a graph of the thermal conductivity K as a function of the temperature T in Kelvin. For example, for 4 metals, silver, copper, gold, and iron. Especially for silver, copper, and gold, we can see that the thermal conductivity does not depend on the temperature very much in this range. Iron depends a little bit more. Then we have the dependence of K on the temperature in the case of water and air. We can see in the case of air, we have a slight increment of the thermal conductivity as the temperature increases. We also know that the metals have a higher conductivity than a liquid, water, and a gas, air. We note here the y-axis is in log scale. Another very important concept in heat conduction is the one of thermal diffusivity. So thermal diffusivity, called alpha, is defined as K divided by rho Cp. So K is the thermal conductivity, rho is the density of the material, and Cp is the specific heat. The thermal diffusivity expresses a ratio between the heat conducted and the heat stored. These are the units, meters squared divided by seconds. The same unit as kinematic viscosity. So the thermal diffusivity expresses the ability of a material to conduct heat quickly, because thermal energy is conducted more than it is stored. If you have a high value of alpha, then heat is conducted much more than it's stored. So it's related to unsteady heat conduction, mostly. Now, let's talk about instead convection. So in convection, only occurs in gases of liquids, so in fluids. They are in bulk motion. And of course, conduction still occurs, but the heat transfer is also and mostly due by the fluid motion. They both play a role. I've sketched here a hot wall. We have a kinematic boundary layer that flows over the hot wall. We inject heat into the fluid and we can sketch the temperature. So we have here a high temperature at the surface of the wall, and we have a lower temperature far away from the wall. In convection, we can distinguish between forced convection, that's due to some external means like a pump or a fan, and free, also called natural convection. That's due to buoyancy forces. So the temperature difference generates the motion that in turn causes convection. I've sketched here the two cases. So here we have a solid at a high temperature, you can imagine, and here we have a fan that generates a motion. So the fluid, gas or liquid, goes around this block and cools it. So the fan gives the motion. So in this case, we have forced convection. Instead, if we remove the fan, but the temperature of the air around the block of a material here is lower than the temperature of this block, then we may have natural convection. So the motion of the fluid is due to delta T itself. Convection is ruled by Newton's law of cooling. So Q dot by convection is due to H times AS times the difference between Ts and T infinity. So H is what's called the convection coefficient. These are the units, watts divided meter squared Kelvin, or we can also use watts divided meter squared C. Because remember, in convection and conduction, we can use Kelvin or we can use degrees Celsius. AS is the surface, the area of the surface. Ts is the temperature of the wall, and T infinity is the temperature of the fluid sufficiently far away from the wall. So at a distance where the fluid does not feel the difference in temperature between itself and the wall. It's important to remember that H, the convection coefficient, it's not a property of the fluid, like the thermal conductivity. It depends instead on the surface geometry, on the fluid properties, but also on the flow regime. So whether we have a laminar flow or transitional flow or a turbulent flow. H values can change quite a lot. So here I've given just some ballpark figures. If you have free convection in gases, H is usually between 2 and 25. If you have free convection in liquids instead, we have a value of H between 10 and 1000. If you have forced convection in gases, we have a value between 25 and 250. A forced convection in liquids, we have an H value of between 50 and 20,000. We'll be studying also radiation. So radiation is heat transfer, forgot an N here, transfer by electromagnetic waves. It's important to stress that a medium is not required, so we can have radiation by electromagnetic waves in a vacuum. And we are particularly interested in a thermal radiation, so the portion of the spectrum of electromagnetic waves that transfers thermal energy. All bodies are at a temperature, absolute temperature in Kelvin, larger than 0, and all bodies emit thermal radiation. In general, radiation is a volumetric process, but we assume radiation to be a surface-only phenomenon. This is the relationship between the temperature of the surface and the Q emitted by radiation. We have sigma AS TS to the 4th power. So this is called the Stefan Boltzmann Law. So sigma is the Stefan Boltzmann constant, so 5.6710 to the minus 8. And also it's important to stress that T, the temperature used in radiation, must always be in Kelvin, because these are the units of the Stefan Boltzmann constant. This is also the radiation emitted by a black body, but this is an ideal situation. So this is the maximum temperature, the maximum heat that can be emitted by radiation by a body at that temperature. In reality, we also have a smaller heat transfer by radiation, so we have to multiply these quantities by epsilon. Epsilon is the emissivity, so it's a non-dimensional number between 0 and 1. So the closer epsilon is to 1, the closest is the value of heat emitted to the one of a black body. So this is for emission of heat from a surface. But of course, we can have some heat radiated that from one surface that impacts on another surface. So what happens to this heat? Well, part of it will be absorbed by the surface and part of it will be reflected. So the portion of heat absorbed by the surface is called Q absorbed, and it's equal to alpha Q incident. And alpha is called the absorptivity and is a non-dimensional number between 0 and 1. So it measures the ability of a surface to absorb heat. Then, of course, because of conservation of energy along this surface, the rest of the heat that's not absorbed is reflected. So that must be equal to 1 minus alpha times Q incident. There is a very neat and simple relationship between the emissivity epsilon and the absorptivity alpha, and the Kirchhoff's law states that these two quantities are equal. In a case of a surface that's in an environment and we have another surface called surrounding, then the Q radiation is equal to epsilon sigma AS times the difference between the fourth power of the surface temperature minus the surrounding temperature. We conclude our discussion today, noting that we can only have maximum of 2 modes of heat transfer. Some examples, for example, in a still fluid, we have conduction and we can also have radiation. In a moving fluid, we can have convection, forced or natural, and this can be combined with radiation. Whereas in a vacuum, we stress we can only have radiation. So that's it today. Thank you very much.